Hello everyone, I am Jasmine and I am student of BTech Software Engineering. This is my identity card and my roll number is 2310994783. Today I am going to talk about the hack CPU and its implementation with HDL code. Let's talk about its architecture. As CPU follows a von Neumann architecture, it means it has a single memory space for both instructions and data. It includes essential components like ALU, control logic, program counter, and registers. And it has two type of instruction like A instruction and C instruction. A instruction is basically to load the constant and C for arithmetic and logical units. It operates on fetch, decode, execute cycle, and where it repeatedly fetch instruction from the memory, decodes them, and execute the appropriate operation. Let's talk about the input pins of the CPU. Here we can see in M and instruction has 16 bit but reset has 1 bit because it is to restart the operation currently working on the CPU. If it is 0 then it will be continuing the currently working operations. Here we have outm, writem, addressm and PC. Outm is the output of the ALU which is to be stored. Writem will allow that if it is one that you can store the ALU of the output of the ALU in data memory register at this location. Addressm will give the location that yes, at this address you can store the output of the ALU. PC is used to fetch the next instruction and work on the current instruction in the CPU. This diagram completely demonstrates how the CPU is interconnected with the data and instruction memory. Here, the CPU receives instruction as input from the instruction memory and accept the value and store it in the register according to the destination which it has D1, D2 and D3. If the 15th bit is 0, then the instruction is A. If 15th bit is 1, then the instruction is C. It will be working on according to that A instruction and C instruction. So let's talk about the API of the chip. We have already discussed it but with the diagram, and here the input pins of the CPU are in M and instruction and the reset, and the output is out M, which is the output of the ALU. Write M is to load. If it is one, that it will store the output of the ALU in data memory. Address M is the location in the data memory that yes, you can store the output of the ALU. Program counter is basically used to fetch the next instruction and it works on the current instruction. It also can jump according to the condition given in the program. Here it has multiple jump condition too. So I have already mentioned that there are two type of instruction in the CPU, A instruction and C instruction. A instruction is basically used to load the constant into registers at the rate value is the syntax of the A instruction, and from the syntax we can tell that it is used to store constants. Then there is C instruction. C instruction is basically used to compute and perform operations on the value given in these 6 computation bits. Here I have given the whole 16-bit instruction and substituted its part, like last 3 is for jump conditions and then D1 to D3 is to tell at what destination these are going to be, and C1 to C6 are the computational bits for the ALU. Then the A is to tell if the instruction memory will be going as the input or the output of the A register will be going as the input in the ALU. 15-bit is used to tell if it is A instruction or if it is C instruction. Then the 13th and 14th are usually negate. We don't consider it as for any kind of program instruction executions. Then we let's come to the HDL code of the hack CPU. We are starting from the parts, and the first gate we are using here is NOT gate. It is basically used to tell if the instruction is C or A. The 15th bit, on the basis of 15th bit we are going to decide if it is 0 then it is A. The second NOT gate we are using, if it is not A then it will be C. because there is only two possibilities, either it is A or either it is B, means the instruction of 15th bit is 1. The Then the AND gate is basically used to check if the output of the ALU is to be stored in the A register, which will be happen on the satisfaction of two things. It should be A instruction, a C instruction, and instruction fifth should be on, means our destination, means our D3, which I have shown in previous slides, should be on, and it will give output ALU to A. Then we have Mux 16. It basically decide what is to be stored in A register using the output of the AND gate. On the basis of the AND gate, A Mux will decide that this is going to be stored in A. Next we have OR gate, which basically decide whether to load value from A register or ALU output. As we can see in the diagram that the output of the ALU is coming back it to be loaded in A register and D register. Then OR gate will be helping next in A register as the load. If it is on, then it will be giving the output in the A register. If it is 0, then it will not be taking the input and will not give the output ultimately. Then we have Mux 16. It basically choose between A register output and input to memory. How it will be choosing? Like I have shown, there was written A in a 16-bit instruction, which is instruction 12th bit. It decides whether the enum will be going as input to the ALU or the A register output. So if it is 1, then the enum will be going. If it is 0, then the A out, means the output of the register A will be going. Then we will be having same as for the A register we used AND gate. Then the means the two sets input should be satisfied, should be C instruction, and instruction 4 should be on, means our D3 should be on for that, and it will give load D, which will be further helping to D register to uh, think that if it is load D is on, then it will give the ALU output, taking the ALU output as input and will be giving the output of the D register. So till now we have seen how the input is going to the ALU and how the instruction is being set. Now we are going to look how the working is going on in ALU. ALU is taking the input from the D register or from the A or M. Either it is A from A register or either it is from the data memory register. It has 6 computation bits and the output of the ALU is ALU out after the logical and computational operation performed on. It will be giving two flags after the output, which is ZR and NG out. Basically, ZR out is the opposite of our out, output of the ALU, as it has NOT gate on it. If the output of the ALU is 0, then it will giving the 1. If it is output is 1, then ZR flag will be 0. NC out is basically for negative output. If it is negative, then it will be giving the 1. Then there is OR gate, which is used for the address where the ALU output will be stored. The next OR gate is for the outem, which is the output of the ALU, means the value that is going to be stored. Then we have AND gate, which needs to be C instruction, and instruction 3 should be on for that, and it will be giving our right M, which is for our load. If it is 1, that it is going to store the ALU output in the address M, which is the location in the data memory. Right M will decide it. Finally, we are coming to PC implementation. It's basically works to fetch the next instruction and jump according to the condition given in the program. So here we can see the first AND gate is being used to checks for 0 flag and instruction bit 1 for ZNE, means here instruction 1, which is our jump 3, we have seen that instruction of 16-bit instruction, like our third jump should be on and our ZR out will be taken as input in it, and it will give the output if jump is equal to, and then the next AND gate will be giving output as if jump is lower than, and for that it will be taking input ng out and instruction 2 should be on for that, means our jump 2 should be on for that this AND gate, and after that it will be giving the output as jump lower than. We can also understand it from the ng out, as it always works for the negative output. And then we will be using OR gate, which will be understanding from ZR out and NG out of two flags and give the whole over output from that, which is with 0 or negative. Either it can be 0 or either it can be negative. Then we have NOT gate, which will be um, ultimately giving the opposite output out of that OR gate, which is going to be positive, because the output is going to be negative or 0, and the opposite of that is going to be positive. Then we have AND gate. It takes the input of the last NOT gate as which is positive, and for that our instruction 0 should be on, means our first jump, means our jump 3 at the starting should be on for that, and input should be positive. Then it will give the output as jump if greater than. Then we will be again having two OR gates for jump equal to and jump lower than. It will be giving jump lower than equal to, jump lower than, jump greater than, and it will be giving to jump to A. Likewise, we have used two OR gates over here. Then again we have AND gate, which will be taking the same instruction and jump to A as the two uh, satisfied condition and giving the output as PC load. Means from here the PC will start working. Till now we have seen that if it is jump, if there is a jump condition or anything going on, then it will give the command to PC that yes, this is the location, this is the condition, here you can jump. And on next NOT gate, PC load will be giving output as the PC increment. Means if not none of, as we have seen that there is some priorities reset, increment, and load, means it gives the most priority to the reset, then to the load, then to the increment. If the reset is on, then it will do the reset work. If the load is on, then it will do the jump condition. If there is none of these two, then it will the last option increment, which is in our last NOT gate. Then the PC will do its work, taking the input of A out and incrementing and taking load, means our whole instruction which is prioritized according to that, and whatever will be on at that time, it will be doing working on those. So now let's talk about the pros of this code, and like it is very concise code, so and it has modularity. So we can see from the modularity that the code is very well organized into functional parts such as ALU registers and control logic, and it also enhances modularity. Each part is responsible for a specific function, makes the code easier to understand and maintain. It does not contain so much information in it, so that too complex the code. And then it has logical structure, means the code is like a roadmap for the computer's brain. It shows how the computer understands and does different tasks, like figuring out what to do with instruction, doing calculations, and this helps how information move around and how the computer make decisions. There is no uh, extra instruction giving in it to make the user or beginners confuse it. Then here, as I have mentioned, it has clear and concise instruction with each part and clearly written, which makes the code more readable also. Let's finally talk about the cons. The first con has limited instruction set, means it is only adhere to some expected format only. The supported instruction set is relatively simple and potentially limiting the range of applications. The second is that it has restricted error correction, which means it does not have that error handling mechanism. Uh, if any unintended error comes into the program, then it won't be able to resolve that, which result in error in the program and it won't run further. So this was all about the implementation of hack computer. Thank you.